All right. Thank you so much, everyone, for being here. Very excited to have Arvid Frydenlund here with us. He is a PhD candidate at the University of Toronto in the Computer Science Department and also at the Vector Institute. His research is awesome. It focuses on language modeling, and I am always really impressed with the amount of knowledge he has and the quality of work that he produces. So really excited here to talk to him about his newest paper, Language Modeling via Learning to Rank. Arvid, welcome.
Thanks. Thanks for having me. And the nice words.
Oh, of course. Yeah, thanks so much. So would love if you could start with an overview of your paper for us, please.
Sure. So the main motivation of the work is that we think that current ways that we train language models using cross-entropy is poor because it only tries to maximize the probability of getting a single ground truth word correct at a given context, right? And it doesn't count for the fact that there may be many other potential words which could continue a context in a valid way. So let's call the words which could form a valid continuation of a context at a given time step, the branching set of a given time step. We then think that label smoothing might be a way of solving this problem, right? Since it would allow us to have multiple targets per time step. However, if you want to implement label smoothing for language modeling, you'd want to do it such that the label smoothing weights would change dynamically per time step over the weights over the branching set. And to do this dynamically, what you would end up doing is just getting a pre-trained language model to generate these label smoothing weights, which is really just a form of knowledge distillation from a pre-trained language model. So we really want to avoid doing that. So instead we propose that we can forego needing label weights at all, so long as we can create an ordering over the labels in the branching set. And then we develop a novel n-gram algorithm to create these branching sets with these rank orderings, and then incorporate this information into the train procedure via a structured ranking loss function.
Okay, awesome. Thank you for that. Now, can you tell us about what the most common ways to train language models are?
Sure. So the way you train a language model is really dependent on the type of language model you're trying to train, right? And there's really three different types of language models. There's n-gram language models, there are neural autoregressive language models, and then there's really BERT as the third one. So when you train n-gram language models, really you're just getting n-gram counts. Then the first type of neural language model, which is the focus of our paper, are the autoregressive, traditional autoregressive language models. And these are trained using cross-entropy, where you try to predict the next word at a given time step, given the previous words as context, right? And then finally, there's BERT and its derivatives, which are really bidirectional language representation models. And BERT makes use of a so-called masked language modeling objective, where a certain percentage of the input sequence is masked. And then you try to, then the objective is to predict the masked out words, right? So you're still using cross-entropy, you're just, the input and the target pairs are now different compared to autoregressive language models. And then there might be like minor variations on these, right? So you might use label smoothing in conjunction with cross-entropy for autoregressive language modeling, which is something that happens, it's pretty standard in, say, machine translation. And then there's a bunch of different variations for BERT, variations on the training objective and variations on the auxiliary costs. Just to go off on a bit of a tangent, I personally avoid calling BERT a language model, even though everyone does call it a language model, since it can lead to some confusing results if you think it's directly comparable to autoregressive language models, which it isn't. So I'll show. Oh, you gotta stop. No.
Yep, stop it. Go ahead.
So in our paper, in one of the tables, we have a comparison between BERT and GPT-2. And you look at the perplexity and you think, well, the perplexity is really low for BERT and accuracy is really high compared to GPT-2. And so you'd think that BERT would be the much stronger teacher compared to GPT-2. The problem is these values are not comparable at all, right? So it's actually kind of wrong of us to put these in the same table, which we do for space. But if you think of them as both being language models, you would look at this comparison table and think that they're comparable. And then the outcome of the paper would be very surprising to you when you find out that BERT doesn't act as a good teacher where GPT does, right? The problem is that BERT really isn't a language model, at least not comparable to auto-regressive language models. Sorry, that was a tangent.
No, that was a great tangent. Is there anything that you would prefer transformer models to be called instead?
Not really transformer models. I think transformers are okay. I mean, I like the name for transformers, it's fine. It's just, I have a problem with BERT being called a language model. I think it leads to some confusion. And the problem is, like, really 80% of it is a language model. It's just that 20% is somewhat of a big change.
Okay. I will share my screen again. Can you explain knowledge distillation to us?
Sure. So knowledge distillation is a method for training models where you have a pre-trained teacher model, and you want to distill the teacher's performance onto a new student model. So in general, the use case here is that the student model is smaller than the teacher model, and hence is more manageable for, say, production as a production model. But because it's smaller, it would be less capable if you otherwise didn't help train with using the teacher's knowledge. So really, knowledge distillation is a kind of train procedure. And the way this is done is that the teacher produces a distribution at every time step, and then the student tries to match that distribution using a KL loss. So now the targets for the student are the distribution over the classes, or words in the case of language modeling. So you can think of this as trying to match the probability of the teacher or the logic matching instead of just trying to match a single ground truth class. However, for our work, we're not using language modeling, or we're not using knowledge distillation for the general use case. Rather, we're using it to solve an annotation problem. Basically, we need multiple potential words for every time step, our branching set, but we don't have these annotations, right? So we use a pre-trained language model in lieu of a human annotator to generate these branching sets for us, or these target words.
Got it. What is rank-based knowledge distillation?
So rank-based knowledge distillation is a pretty intuitive extension to traditional knowledge distillation. So instead of matching a distribution, we can convert that distribution to a rank ordered list, right? Most probable to least probable words. And then we just try to match the ordering of that list. So in particular for our work, we truncate the list to the top K best words, and then we try to match it using the Paquette-Luce rank loss, which is a structured ranking loss. So just to take us back to the beginning for a little bit, in our original framing, or our original train loss, which is cross entropy, at a given time step, we're trying to predict a singular ground truth word, right? In traditional KL-based knowledge distillation, the teacher generates a distribution over the entire vocabulary, which we're trying to match. However, then in rank-based knowledge distillation, the teacher generates a top K ordered list, and we're trying to match the ordering of that list.
That's good. And why is that important?
So this is a really good question, and one that we don't actually fully explore in the paper. It's important for us because the n-gram algorithm that we use is incompatible with traditional knowledge distillation methods, right? So we need it as a result of trying to use our n-gram method. But it does actually have some information that it is capturing in terms of the structure of the problem, right? So really what happened is we had this annotation problem, right? Where we're trying to use a pre-trained language model as a substitute to humans having to annotate these branching sets. However, then this means that we have to use a language model to train a language model, right? And that's not really a great constraint that we want, right? So then we developed this n-gram algorithm, then we thought that n-gram language models would help us with this problem. The problem is n-gram language models produce a fairly weak distribution. So if we just try to match that distribution using traditional knowledge distillation, we're gonna get really poor students, right? So then we rethought what's actually going into the n-gram language model and kind of stripped it to its bare bones and got this novel n-gram algorithm, right? The problem is this novel n-gram algorithm is a non-probabilistic model, right? So we don't have probabilities that we can match using traditional knowledge distillation. So we have to use rank-based knowledge distillation to actually be able to use that method, right? So the reason why we're using it is out of necessity for our methods, right? However, it is actually capturing things that other methods aren't doing, and we can see this in prior work. So the first paper that I know of doing rank-based knowledge distillation is an AI stats paper from last year, and they apply it to actual ranking tasks, right? So that the teacher is a ranking model and the student is a ranking model. And then they show that rank-based knowledge distillation does better than traditional KL-based knowledge distillation when your task is actually a rank-based problem, right? So that makes a lot of sense that you can do that. And in general, ranking is just a form of structure prediction, and you can have very different kinds of structures, right? And so there's lots of other papers that do structured-based knowledge distillation where they're trying to capture this structured information, right? So to answer the question, there's really two reasons why you do this. Is you either have a structured problem that you're trying to capture this structured information, or you can apply it to knowledge distillation problems where you can't otherwise for traditional knowledge distillation.
That's very exciting, Arvid. You also use an n-gram algorithm to create a non-probabilistic teacher. I think you touched upon this quite a bit, but is there anything else you want to add? And can you tell us about how this helps with training and why it's efficient? Yeah, so really it's just getting us our annotations that we lack, right? Again, you could think of having a human annotate these for us, but that would be way too expensive and time consuming. So we're trying to bootstrap our information using this n-gram algorithm, right? And again, we could also use a pre-trained language model to do this, but we don't want to do that because then you have a language model that needs to train a language model, right? In terms of the question about why it's efficient, there's various ways you can kind of unpack what it means to be efficient, right? It's efficient. The algorithm that we created is efficient, and it only needs to be done once to create these n-gram branching sets before training our student model, right? And then we can incorporate this information into training our student language model efficient using an efficient GPU implementation of packet loops, right? So it's not costing us anything in terms of computation to be able to do this. But there's actually a more interesting idea in terms of efficiency that we don't really touch upon in the paper. But the idea is this, that the n-grams are collected from global statistics over the trained data set, right? So in comparison, when you just train using regular cross-entropy training, you're only ever doing a local procedure where you're using local information to update a time step at a given time, right? Using that local information. But when you introduce these ranking information, either from the n-grams or from the pre-trained language models, you're introducing global information about the trained data set into your local training procedure. And so it could be that there's actually a training efficiency there, but it's not something we actually explore in the paper, though we do mention it. Okay, awesome. And I guess you also don't have to spend millions of dollars training these gigantic language models,
yeah, exactly. Yeah, that's also kind of like a future work that we kind of talk about. But one of the efficiencies there is you can kind of bootstrap yourself using these n-grams, which is really just a rule-based system. So it could be that it helps for like cases where you don't have a lot of data, right? Where you're making these extra targets that you wouldn't otherwise have from this rule-based system, right? So you don't actually have to have an annotator annotate your otherwise small data sets, right?
Mm-hmm. Yeah. You found that GPT-2 is a better teacher than BERT and also born-again models. Can you describe the difference between these three models and why GPT-2 makes for a better teacher? Sure.
So the born-again models are kind of a strange thing. Basically, they're the case when your teacher model is the exact same model specification as your student, right? So it's kind of a self-distillation. And the surprising thing here is people have found that this self-distillation actually improves your student performance, right? So you just train one model, then you go back and train it again using the same model as now the teacher, right? So that's what the born-again models is. GPT-2 is an autoregressive language model, like our student models that we're trying to train are. And BERT, again, is not really a language model. Like I said, it's a bidirectional language representation model, right? So the reason why we chose these 3 different models is because of first a data leakage issue, right? So GPT-2 and BERT are trained on a bunch of extra data that the born again models and our n-gram models are not trained on, right? The born again models and the n-gram models are just trained on our actual training data set, where GPT-2 and BERT are using a whole bunch of extra auxiliary data, right? So that's why we want to use the born again model here, is because it allows for a better comparison with the n-gram model, right? But because of this, the born again models are not going to be very good models, right? It's the exact same model as the student, right? So that's why you don't expect them to be, you expect them to be much worse than GPT-2, right? So then we also want to use GPT-2 and both BERT because they are different types of models, right? So BERT uses future information. And so we thought that it might produce better ranking ground truths because it's using that actual future information. And this turned out to actually be a problem why it performed fairly badly. So I can actually show my screen again to show some examples of this.
Please do.
Is that sharing?
Yeah.
Okay. So in the appendix, let's find an example. Yeah, so here's a good example. So here the ground truth sentence ends in museum and then a period. So the sentence actually stops there. And so because BERT sees future information, it knows that that sentence is actually ended. And so it doesn't actually try to continue the sentence, right? It puts it as end of sentence, or it tries to make it like a new header, right? This is also the header marker in our data set, where GPT-2 actually just tries to continue the sentence, right? So this is going to be a mismatch between our how our student models, which are autoregressive, which will try to continue the sentence, right? It's a mismatch between the what you could call the downstream task that we're actually evaluating our students on, right? Where GPT-2 actually matches this task, and so it doesn't actually have this problem, right? There's also other issues with BERT. So it also had like a orthography issue where it really liked to try to match examples of the orthography instead of matching words that would be similar. So where GPT-2 matches similar words that could continue with this tried to matches the and the as like capitals, even though this would be like very ungrammatical in the middle of the sentence, right? So it's trying to match how the word looks instead of the function of the word, which was an unexpected thing that BERT would do. Again, so like in with a capital, Ini. So Ini is actually an Egyptian goddess name that's just matching because it looks like in, where GPT-2 actually gets the grammar of the word.
Wow.
And then you can see that n-grams also gets this pickup, right? So we don't actually need our pre-trained teacher model to be able to get the second rank, which also matches GPT-2. And same with numbers, they'll expand it.
That's really interesting.
Yeah. Again, that was kind of a tangent, but I think that answered the question.
Yes, it did. Thank you for that. Okay. And would you expect GPT-3 as a teacher to give about the same results or better?
It would probably do better than GPT-2. Again, that's going to be probably because it's a better model in itself and because it's trained on better data, right? Mm-hmm. But this kind of question is not really necessary for our work, right? So our work, we're trying to talk about how you could actually distill something, not what's actually being distilled, right? So yes, it would do better. Our student might be do better, but it's just because it's distilling better information, right? That's not actually talking about the process of being distilled, which is what we're actually experimenting on. Mm-hmm. But in general, if you actually wanted to apply our methods to a real application, yes, you'd probably want to pick the best teacher, which would probably be GPT-3. Yeah.
Makes sense. And can you describe the experiments you ran to come to this conclusion? You already described quite a few of them, but if there anything else that you want to highlight?
Sure. So like I think that experimental, I can show the screen again.
Sounds good.
like we have this really big table that's kind of confusing. And it was a really big table, not broken up for paper space reasons. But it's really trying to show two ideas here. Where are we? Yeah, it's a big table. So kind of going back to the motivation of the paper, we want a better training method for language models. And we think we can do this making use of multiple targets per time step. And then we really have two problems. We have the problem that how are we going to get these multiple targets, which we do using either the pre-trained language models or our n-gram model. And then for the second problem, we have how do we actually incorporate these multiple targets into the train procedure, right? Which we do using the Plaquet-Luce rank loss. So then we have two questions, right? We have two questions. How well are our pre-trained language models or our n-grams doing in comparison to each other, right? How well are they actually creating these branching sets? And how well is our rank-based knowledge distillation using the Plaquet-Luce rank loss actually doing compared to traditional knowledge distillation and to traditional cross entropy, right? So the experiment setup is kind of, we're comparing everything to our cross entropy baseline. And basically everything, or like at least all the cases that we actually care about do better than the cross entropy baseline. So there's multiple Plaquet-Luce losses here. This is kind of a detail in the paper that you can look up in the paper. In general, you can think of these as being all the same kind of Plaquet-Luce, and one Plaquet-Luce will do better than the cross entropy, right? It might not be the case for everyone, but one version of Plaquet-Luce will do better. And so then we find that knowledge distillation always does better than cross entropy, either if it's rank-based knowledge distillation or traditional KL-based knowledge distillation. And so then we have the other question of, or we have the question of, does rank-based knowledge distillation using Plaquet-Luce do better than KL-based knowledge distillation? And this is actually a surprising result. So we find that in the majority of cases, it does do better than our traditional KL-based knowledge distillation. But this wasn't something that we actually expected to find, right? So what I was expecting to find would be that it would actually do worse. And then I wanted to actually quantify how much it was doing worse so that when I applied it to the n-grams, I could say, yes, you're losing a little bit of information using the rank-based knowledge distillation, but it's not that much. And then we can actually do the comparison between the n-grams and the other teacher models. So this was like a happy accident that we found that actually did better than traditional KL-based knowledge distillation, at least for our specific tasks, right? And so then now that we know that we can do this rank-based knowledge distillation, we can then apply it to the n-grams and show that the n-grams perform better than the born-again models, better or comparable to the BERT models, and not as well as GPT-2. But again, this is really to be expected. Like the n-gram method is like a really dumb method, right? It's a very naive method. So you'd expect it to do worse than the very strong language model GPT-2. And so the fact that it actually does as well as it does is the surprising result.
Mm-hmm. Got it. That is a very interesting result to have found. Really neat. We do have more questions, but we are coming to the end of the session. I'd like to give 5 minutes to ask questions. And if there aren't any, I'll keep asking you more questions. Does anybody want to plop any questions in the chat? I'll give it 30 seconds and then I'll keep talking. Okay, I'm going to keep talking. Thanks for that, RV. Can you stop sharing your screen? Oh, there we go. Okay. All right. So, what do you find the most exciting about the findings you presented?
So I think the major find is that rank-based knowledge distillation might be applicable to tasks that aren't really considered as ranking problems, or from teachers that aren't really models, right? Our n-gram algorithm isn't really a model in the traditional sense. It's a set of rules to generate targets, right? So the major contribution to this paper is that we're taking the problem of language modeling and reframing it as a ranking task. And then when we combine this with the n-gram algorithm, what we're really doing is distilling a rule-based system, right? So we have this rule-based inductive bias that we think will help with training. And we use this rule-based system to generate these structured targets, which help augment or support our original training targets, right? So then you can incorporate this informative set of rules into the model via the training procedure without actually having to modify the model at all, right? And I think this would actually be a fairly general setup that would maybe be applicable to a lot of problems outside of language modeling. Yeah, that's probably what I'm most excited for. Is I think it is a general framework for incorporating rule-based systems into training a neural model.
Do you have any future work you're planning on that aspect?
Yes. So one of the things I didn't mention in the paper is there's a problem called the representation degradation problem, which happens when you train a very skewed multi-class system using cross-entropy training. And I'm thinking training language models via learning to rank might actually help this issue when it appears in language modeling. Since I'm talking to you, one of the other future uses that I mentioned is that it could be used for black box knowledge distillation. So say you expose a model via an API that just gives you the top K outputs, right? Well, you can now do knowledge distillation from that, what would otherwise be a black box model, right? And I imagine that would have some privacy concerns. Not that I know a lot about privacy, but.
That's interesting. That could definitely have a lot of privacy concerns. You should talk to Nicolas Podokpevno's group. I bet they've seen that. Okay, I do want to go on to the next slide, but my slides are flipping out on me. That is because that is the last question. Okay. So we do have 1 minute left. Would anybody like to ask questions in the last minute? Stunned silence. Well, I personally had a huge amount of fun chatting with you, Arvid. Thank you.
Yeah, this was great. Thanks for having me.
Yeah, this is really exciting work. Very happy to have learned about it. And yeah, thank you for joining us. And thanks everyone for joining us in the webinar.
Thanks.
Have a great day.